Is that clear? Now, let us look at the magnitude responses of these filters for various values of QP. So, so what is magnitude of h of j omega? Is 1 over square root of 1 minus omega square by omega p square whole square plus over qp square. Okay. All right. So, so this is I mean you can expand this in the following way. We just do this. This is nothing but 1 minus 2 omega p square, sorry, 2 omega square by omega p square plus omega to the power 4 by omega p to the power 4 plus omega square by omega p square times qp square plus omega to the power 4 by omega p to the power 4, right, which is basically I can combine these two terms and write them as one plus omega square by omega p square times 1 over qp square minus 1 minus 2 plus omega by omega p whole power 4. Okay. So, for omega by omega p much smaller than 1, right, you know, which of these two terms, I mean, which is larger, omega by omega p the whole square or omega by omega p whole power 4? Whole square is much greater than omega. So, basically you see that for omega by omega p much smaller than 1, mod h of j omega the whole square, so that I can avoid writing the square root, is nothing but 1 over 1 plus, what is it, omega square by, I mean we can neglect the fourth order term, and then this is nothing but 1 over qp square minus 2, correct. So, if this is positive, so if in other words, if 1 by qp square minus 2 is greater than 0, for small omega by omega p, how will the magnitude response look like? So, this is omega by omega p, this is 1, let us say. For small omega over omega p, for 1 over qp square minus 2, at DC what is the gain? At DC it is 1, very good. So, if 1 over qp square minus 2 is greater than 0, what comment, how will the magnitude response look around DC? It will be less than 1, it will be less than the gain at DC. Okay, so it will do this, correct. So, this corresponds to, I mean 1 by qp square minus 2 less than, I mean greater than 0 means that qp is less than 1 half. Less than 1 by root. So, this is QP less than 1 by root 2, you will have the response drooping like this. For QP 1 by QP square minus 2 less than 0, how will the response look like? The coefficient of that omega square by omega p square term will be negative, and therefore, it will increase. So, this corresponds to QP greater than 1 by root, right. So, for exactly QP equal to root 2, what will happen? I mean, this is only at 0. Remember, we have neglected the 1 by omega p whole power 4 term, right. So, around DC it will look flat. This corresponds to QP equal to 1 by root 2, right. So, for the special case of QP equal to 1 by root 2, all right. What comment can you make about mod h of j omega square? For the special case of 1 over QP being equal to for QP being equal to 1 by root 2, what happens to this term? That becomes 0. So, what remains in the transfer function? 1 by 1 plus omega over omega p whole power 4, right. So, around DC it is flat, it is not changing, but eventually as omega by omega p starts becoming larger and larger, what happens to the transfer function? It will decrease. So, at omega by omega p equal to 1, what will be the transfer function? 1 by, at omega by omega p equal to 1, what will be the transfer function? That is a square magnitude here. 1 by root. So, basically right. So, basically at this thing, this will be 1 by root. Okay. So, in other words, choosing q less than half makes the response around DC droop like this. Choosing q greater than half causes the response to go up like this. Eventually, what must happen to the, regardless of the value of q, what comment can you make about the response as omega tends to infinity? To what? To 0. So, regardless of the value of q, eventually the response must go to 0, right. So, basically this is at DC, and this is, let us say, omega over omega p. So, for very small q, so for example, and okay. So, yeah. So, what is the magnitude at I mean, and staring at this is just another observation. The magnitude of h of j omega p is what? We just need to plop in omega equal to omega p in that expression and calculate what that magnitude response is. Please calculate it and tell me. It is QP. Very good. All right. So, we know that the DC gain is 1. The gain at omega p is exactly QP, and the gain at infinity is 0. So, now we are in a position to plot the magnitude responses for various values of QP. So, for QP less than half, we know that already we know that the response is going down like that. At omega p, the value is QP. In this particular case, it's half, right? And then eventually the response must go to 0, right? Now, at for QP this is QP less than QP equal to half. So, for QP equal to 0.707, which is the special case of 1 by root QP being equal to 1 by root 2, what happens around DC? The response is not drooping like this; it is actually flat, right? And the response basically looks like this. And at omega by omega p equal to 1, the magnitude response is 1 by root 2. So, eventually this must also go to 0, correct? All right. Now, when q is greater than 1 by root 2, what happens? What comment can we make? Well, we saw that at DC the response is going like this, and so for q for example being say 1.5 for instance, um, so the response, the magnitude, the gain at omega equal to omega p will be 1.5. We know that the response around DC is doing that, right? It does something like this, and then does that. As you keep increasing q to higher and higher values, what comment can you make about the gain at omega by omega over omega p? At omega equal to omega p, the gain will become higher and higher and higher, right? At q equal to qp equal to infinity, what will happen? The gain will just go to infinity, and that makes sense because there are two poles on the j omega axis. Okay. So, this special case, namely QP q is equal to 1 by root 2, results in a response that can be as flat as possible at DC, right? Choosing any other q will either make the response droop like this or peak up like that. So, this is the such a response is called a maximally flat magnitude response. Right, also are also called the Butterworth response. So, this corresponds to a second order Butterworth filter. Does it make sense? Okay. So, the for a second order Butterworth filter, what is the 3 dB bandwidth? Is what? Is simply omega.